Okay, so today finally we finally have enough background to talk about the optical gain in the semiconductor. So let's start with the definition and the expression of optical gain, and then we need to really calculate what the optical gain is in numbers. So it's no more a conception. We want to know what the exact value of the optical gain, and then we will gonna revisit some parallel the effect in the spontaneous emission and some many body effect that only happens when the carrier density is really high. So let's define the term of optical gain. We can start with the term with optical loss. This is a Beer-Lambert law. Means if a material is absorbing light, so we call this a piece of material, and shift it a little bit. If a piece of material is lossy, that the incoming light is I0, and it will decay exponentially, and it will be expressed as the intensity I of x is I of 0 exponential minus alpha x. This is the Beer-Lambert law probably you encountered in the chemistry class. However, if a material is excited, semiconductor excited, so it has a high carrier density. So the material is actually propagating exponentially. So we can write it down as I of x is equal to I of 0 exponential gx. Instead, that means the intensity is propagating. So if we do a derivative at both sides, and since I it can be expressed as the number of photons. This is the terms of energy, and a photon is also an increment of energy. So we can write it down as like NP is NP0 and the exponential g of x. If the material is providing gain, then the NP over dx is equal to g NP exponential NP0 g of x. So it's g of NP. Okay, so we can define the term g by the distance derivative of a light of a photon number while the light is propagating in such a material. So we just put the NP to the other side. So we get that G could be described as the 1 over NP times dNP over dD. Alright. And we learned the optical transition in terms of time. So we can imagine this is a piece of semiconductor with under excitation, and this small piece has a distance of delta d. So while optical mode propagating through that, the material, the energy passing through will be equal to its velocity times the time it resides during this small delta d. So we can change the dD to be its true velocity with a small time. Because if the light passing through the material, it doesn't interact with that anymore. So now we can shift the dD into over Vg dt. Okay, So it is 1 over MP over Vg. And what's the MP over dt of a specific position? It will be the net recombination rate at that position. So that will be R21 minus R12. R12 is the photon is absorbed this material from the convention valence band to conduction band. Then R21 is the transition rate for a carrier undergoing the downward transition from conduction band to valence band. And the R21 is positive because it gives you more photon in the cavity. But R12 is negative because it will absorb light, so the photon density is reduced. And luckily, we know that R21 and the R12 is a pair, and pair transition with the same radiativity constant. So it can be further reduced as RR, the term we learned from Fermi golden rule, times F2, the probability of a carrier in higher level, minus F1, the probability of a carrier populating in the lower level. So if F2 larger than F1, which means you are pumping it so hard, so the probability of a carrier in higher level is even more than that one in the lower level. So it's called population inversion. So when population inversion happens, you get a positive gain for a specific the absorption and the stimulated emission with a specific h nu. So with different frequency of light, it will matching different pair interaction in the conduction band and the valence band. So for the one in the band edge, the transition between these two will dominate. You will care about the F2 at the EC and the F1 in EV. But if the incoming line has a stronger, higher energy, for example, it matches the transition from this position to such position, then that will be the F2 of the energy at higher level in the conduction band, and the F1 of the probability in the lower level. So the probability definitely will change. So F2 minus F1 will be a function of the photon energy. So the gain is a function of wavelength. It becomes a gain spectrum. Yeah, because you can calculate the gain at one point, at one energy, and then you plot every point, then you get a gain spectrum. So let's see, let's dig down and trying to simplify to eliminate all the unknown parameters in the equation. First is the group velocity. The group velocity stands for the propagation of the energy packet, not a specific way. So its relation to the speed of light is normalized by the group refractive index. The expression is the relation with the phase group refractive index, written down as following. Ng is n minus lambda En over d lambda. So that far. So for refractive index, it's with its wavelength is usually plotting like this. And the highest position is the band gap, e.g. in lambda. So we are doing the part with the transparent one. So the light to be longer than its band gap, or the light will be absorbing. So at this part, it's obvious n over d lambda is less than 0. So for the part denominator less than 0, so this is a plus term. So it should be higher than its phase index. And how high is that? It's usually 1.3 to 1.4 is phase index. It's just like a empirical experience. Is 3.5. Ng is usually 4. So this is for like a 490 nanometer for GAAS. So while you're doing the calculation, you remember you need to calculate the gain with the group refract index most of the time. But in the following one, because we trying to, so it will be different. While if there's n is the phase index. So with the G in the bottom is the group index. So while you reviewing it, you need to take care of that. Sometimes it will be misleading. Okay. So anyway, so let's continue to expand that. So first we remove the VG, because the VG is something that we usually don't have the number, but we can evaluate the group refract index as long as you have its dispersion relationship. You can calculate that. Okay, then we need to expand RR here. So RR this is the Fermi-Golden rule. So R is 2 pi over H bar. H21 squared like low R, and this is the reduced density of state. Since you can only count the vertical transition. It will also refer to the lecture 3. Yeah, lecture 3 or lecture 4. And this is the momentum matrix. And the momentum matrix is a relation of this. This is the transition matrix element, and usually relevant to the momentum matrix element according to the polarization of light and the heavy hole or light hole. This is what we talk about in the lecture number 4. Yeah, the second radial transition. So if you want to more detail, you have to review the older material. Alright, anyway. Then we just put everything into the relation here. It turns out a very long equation looks like this. 2 pi over h bar times QA0 divided by 2m0 squared times momentum matrix element divided by MT group dozen. Then times is reduced density of plate, then times F2 minus F1. Okay. So when the first time you see that, you might feel a little intimidated. But and the word is still not good enough, because there is still something you don't know. What is NP? This is pretty conceptual. The number of photon density. But if you ask me to give a number of that, okay, difficult. Second, we do the vectorial field in order to solve the Schrödinger equation, and in a steady state. But we also have no idea what A is. It is still not enough to calculate numbers, so it actually needs further simplification. Okay, so let's take a deep view. What the A is. First, this is a plane wave. Because while the light is propagating into the solid and interacting with a specific carrier near its environment, since the wavelength of light is pretty long, and the wavelength of the carrier is very small in two different sides, so you can actually treat all the optical wave for a carrier as the plane wave because the curvature is very different. Yeah, while you're doing the long distance, probably you're doing the length. Yeah, you will feel okay. This is a plane wave. This is a spherical wave. But while for a small carrier in the solid, facing an electromagnetical wave with a wavelength much longer than him, you can always treat it as a plane wave. That's not exactly, but pretty good enough approximation. So let's start with that. Just treat the light for the carrier as a plane wave. Then this is the definition of the vectorial field. Okay, simple ordinary equation. We just do the partial t and do a time integral. So now the A is E0 divided by I omega. Still a plane wave, but with a phase shift. Alright. Then we do square at both sides. So we have E squared, the energy, the electric field intensity should be omega squared times A squared. Okay. And this is the Poynting theorem. What's the optical density in the material? It should be half of 1/2 times. This is not the typo. Yeah, one is N, one is Ng. The half of 1/2 times refractive index times group index. Axiom 0, vacuum permittivity, E squared. Alright? And the thing we know that E squared is equal to, but the E squared is equal to omega squared A squared. And the such density should be counted as number of photons. So it should be NP times H bar omega. Alright, so this is very useful because we can now put A squared over NP at one side. The rest of the depth in the other side. So A squared over NP is equal to a bunch of constants. Then let's go to the same equation in the left page. There's the A squared. There's NP. Okay, then we replace that with this bunch of constants. Then this H bar omega be written as H mu. Yeah, this is just one the common constant times is frequency. And the Ng times Vg is the light of speed. It's still a constant. Okay, then we can put all the constant in the big bracket. Second times is momentum matrix, transition matrix element divided by its photon energy times reduce the density of state times the population factor F2 minus F1. Okay, so it's still very long. It's still a difficult thing to calculate, but we can keep simplifying that. So the first one is all constant. It's pi q elementary charge. Reduce the Planck constant to N. So only the N is a material constant that might change from material to material. And the rest of them are all universal constants. So we can simplify it to the actual sum calculation is 1.097 times 10e minus 16 divided by its refractive index. Okay, so now the first thing is done. Second is this one, 2mt over m0. We can do the 2mt over m0 further. 2mt squared over m0. Put it the momentum matrix at both numerator and the denominator to make it like m squared m squared times 2m squared over m0. Okay, this is a material constant, momentum matrix element, and this depends on the polarization of light. Polarization as valence suspend. Okay. For example, if it is 940 nanometer constant and the material is InGaAs with 20% indium, then okay, so there's a table here. InGaAs with a 20% indium, that means X is 0.02. Then it's 2m squared over m0 is okay 28.8 minus 6.6 times 0.2 in EV. Okay, since the units is important. And the lasing mode, if for most of common term, is dominated by. Okay, I didn't example that. Yes, for semiconductor laser mode is usually dominated by TE mode with the CHH and the CHH. CHH means the transition between conduction band and the heavy hole subband. Okay, so in this case, for the M squared over n squared is 0.05 near gamma hole, near the band. So that's also a figure we learned from the lecture 4. This is the increment vector in the band structure, and this is the transition strength normalized by the momentum matrix element. So this is a C1HH1. That means the first ground state in conduction band with the first ground state in heavy hole. And while the K is near expand edge means K near to 0. The TE mode transition is about 0.5. That's usually the number we care about because we usually want to lay around the band edge, since that will be the wavelengths achieve population inversion first. Yeah, we usually don't want to make a lacing at the very high the current density. That's not normal. Okay, so usually for CHH1 transition interacting with TE mode, the transition strength is 0.5. So this term becomes 0.5 times the material you choose. 28.8 minus 6.6 x in EV. Okay, so this is the second term. So it depends on the polarization and band structure. And the third is this is simple. This is what's the interest wavelength. So if it is 800 nanometer, then you can calculate transform that into EV by the simple equation. 1024 0 nanometer divided by wavelength, then you have 10 meters. Okay. And the reduced density of state needs some calculation. We will practice that later. But we already reviewed that, but we haven't really tried to calculate that. Then F2 and F1. The number of F2 and the F1 depends on where the quasi-Fermi level is. So it is a function of injection carrier density. With a higher injection carrier density, you have a larger delta EF. Then your F2 minus F1 eventually goes from negative value to positive value. Okay. So then we have so we can further to reduce that to even only one number, because only this term is a function of carrier injection level. The rest of the term is determined while your device is made. Yeah, because if you might choose to make an InGaN laser, INGS laser, INGS laser, but since it is made, those are all just constants. Yeah, so after you calculate that, actually all of them is a bunch of constants. So we can further reduce going to that. So the Gmax is actually the gain of a specific wavelength is a maximum value Gmax that we have to calculate after solving that term by term. Okay, so it is tedious, but after probably one of you the practice is actually just fine. It is just difficult to calculate, but it's probably also difficult to understand. But if you after you took few courses, just repeat the video 1 time and 2 times, actually that's just one thing. Alright, so the gas spectrum can give you something like that. A maximum value for specific wavelengths times F2 minus F1. Alright. So let's consider what's the maximum and the minimum value of your gain. So if there's no any injection and at a very low temperature, all the carrier density, all the carrier in its lowest carrier energy level. So what happens at such level? That means there's almost no carrier at high energy level, and the fully filled in the low energy level. In this case, F2 should be 0, and the F1 should be 1. So the gain spectrum will be F2 minus F1 will be minus 1. So the minimum value is a negative value. It's called minus Gmax. That's the case of the absorption, the Beer-Lambert law. So you can also refer this number as alpha. So that will equivalent to the absorbance of a material of a semiconductor. However, if you excite this material or pump the material really hard, either by giving injection current or shining it with a strong laser to make a lot of carrier pumping from low level to higher level, then what might happen? That will make the quasi-Fermi level high, and the quasi-Fermi level for conduction band at a high level, and the quasi-Fermi level for the valence band in the lower level. So this is the conduction band and the electrical. Under no excitation, EF is here, and the probability should be like this. This is the F, and this is the E. So at this low level, F1 is almost 1, and F2 is almost 0. But under a strong excitation, for example like this, And now you get the two Fermi level. Since the excitation is high, so let's call this is the E, F, C, and probably E, F, B, something like that. So for something like this, so at this level, F2 is almost 1. This is the Fermi-Dirac distribution. And similarly, for this level, F1 is almost 0. Since you completely really hard to make the Fermi level separate. Then you are looking for the transition between here and here. Alright. So under this extreme case, it goes to F2 close to 1, F1 close to 0. So its gap is Gmax. So this value is could vary from material to material, but it doesn't go too far. It's usually in the order of 1e4 to 1e5 per centimeter square. Why? Because all of these terms, actually most of them are common constants. What might change from material to material? First, refractive index. Second, reduce the density of state. This is most relevant to the effective density, effective mass of the carriers. Yeah, since they might vary from, for example, the number of the density of state is low in gallium arsenide, but quite high in the gallium nitride. But that doesn't change very far. Probably 10 times higher is already very high. So the whole term for all common material have a close range of its Gmax, and it's highly dependent by its since the MT is also since if you're doing the C1 with H1, the MT divided by M squared is also pretty close. Yeah. So the most influencing factors, one is original momentum matrix element. Second is effective mass of the carriers, and its refractive index. The rest of them are almost all constants. So the gap usually ranges at this level from around 1e4 to 1e5 minus 1. So it has a minimal range and a maximum range.